Welcome. We are going to discuss about the Taylor series for function of complex variables. So we start by stating the series and then giving the proof. Thereafter, we'll do some examples on the same. So Taylor series. So our interest is to discuss Taylor series with respect to function of complex variables. And the structure looks more or less the same as the Taylor series for function of a real variable. So the statement of the series or theorem, if f of z is analytic inside a circle, so that's the Taylor series for function of complex variable. So if a function f of z is analytic inside a circle, its center at A, then for all z inside this circle C, f of z is given by this series. So this is a main statement. So I provide the proof for this. So proof. So we consider z to be any point inside the circle C, then construct another circle C1, which contains z in its neighborhood, such that this new circle C1 has a radius less than the radius of the circle C. So this is what I mean. So let's then construct a circle C1, which contains this point. So this is what you mean. So this is the main circle, C. Then, so this is what you're calling the circle C. So we have a point Z within this circle C. So we construct another circle C1 inside this main circle. So this is a circle we are calling C1, such that on this circle is a general point T. And then within this circle, we have what we call the point A. Clearly, the radius of C1 is less than the radius of the circle C. Then by Cauchy integral formula, by Cauchy's integral formula, we know that f of z is given by 1 over 2 pi I integral. If we do the integration along C1, then we'll have f of t divided by t minus z dt. So remember, generally the Cauchy's integral formula is the nth derivative at a point A is n factorial over 2 pi I integral along a certain circle, f of z is z, then divided by z minus a power n plus 1. So if we are doing we are defining so remember the zeroth derivative is the same as the function itself. So from this general formula is what gives us this expression for f of z. Now carrying out integration along C1, that's why the variable here is t. So we have this fraction 1 over t minus z. We can write it as 1 over t. I want now to introduce the a into this expression. So I can smartly write this as t minus a, and then minus z, and then plus a. So check that this new expression I've written is exactly the same as the original one, but I'm just trying to rewrite it in such a way that I can take care of the point z equals to a. So which can be written as 1 over t minus a minus, now when I factor out negative, so I'll have z minus a. So this will be the expression. So therefore, we divide each term in the numerator and denominator by t minus a. So in this new expression, so this, I mean that 1 over t minus z, which is the same as 1 over t minus a minus z minus a, is the same as 1 over t minus a divided by t minus a minus z minus a over t minus a, which will give us 1 over t minus a divided by 1 minus z minus a over t minus a. So which can be written as 1 over t minus a into 1 minus z minus a over t minus a, then raised power negative 1. The question will be, why are we struggling to do this? The reason is we want to rewrite this fraction 1 over t minus z in such a way that we can get an expression which can be expressed as a binomial series. So with this, so this what is 1 over t minus z. So we know that uh, 1 minus x power negative 1 is the same as 1 plus z squared plus x squared plus x squared plus x cubed plus x power 4 plus x power n. So this is binomial series. And this works whenever the absolute value of x is strictly less than 1. We are going to make use of this aspect of the binomial series of expansion of the expression of this form. And you see from our diagram, it's very clear that the distance from z to a, from this diagram here, should be clear that this distance from z, t general point on the C1, if I call it R1, and this distance from z to point A, which is within the circle C1, R2, so R1 is greater than R2. So which means in this quotient, z minus a over t minus a, z minus a is less than t minus a, so we expect the absolute value of this quotient be less than 1. So which makes it possible for us to expand this expression as a binomial series using this formula. So therefore, we have by binomial series of theorem, one over t minus z will be 1 over t minus a into, so this one, the role of x here is taken by z minus a over t minus a, so we should be 1, and then plus z minus a over t minus a plus z minus a over t minus a squared plus z minus a over t minus a power 3 plus z minus a over t minus a power 4 plus other several terms. And this is valid since z minus a over t minus a, absolute value of this quotient is strictly less than 1, can be clearly seen from the diagram. So therefore, now going back to, if I call this one 1, so going back to equation 1, let me call this one 2. So using 2 in 1, we get, so f of z will be given by 1 over 2 pi I integral along C1 f of t z t minus z dt will be given by 1 over 2 pi I, then integral along C1. Then remember this part, if I have f of t over t minus z, can be written as 1 over t minus z times f of t. So therefore, I'm going to write, instead of writing 1 over t minus z, I write what I have in 2. So I'll have into brackets. So I can actually put this t minus a inside. So the first one will have 1 over t minus a plus, so next one I'll have z minus a, but t minus a will be raised power 2 because this is power 1, this power 2. So power 1, this power 2. So z minus a over t minus a squared. Next will be z minus a, then squared. But remember, here I have a square. So this numerator squared, denominator square, then multiplied by this will be t power 2 minus a power 3. So t minus a power 3 plus z minus a power 3 over t minus a power 4 plus z minus a power n over t minus a power n plus 1 then times f of t, then dt. Opening, we'll have f of z will be 1 over 2 pi I. So the first one, I'll have integral along C1 of, so this multiplied by f of t, so I have f of t over t minus a dt plus 1 over 2 pi I integral along C1. So I have z minus a over t minus a squared, then times f of t dt plus 1 over 2 pi I integral along C1 of z minus a power 2 over t minus a cubed f of t dt, and then plus 1 over 2 pi I integral along C1 z minus a power 3 over t minus a power 4 f of t dt, all the way plus 1 over 2 pi I integral along C1 z minus a power n divided by t minus a power n plus 1 f of t dt. So this is the structure of the integral. But remember, from definition, the Cauchy's integral formula is nth derivative at a is n factorial over 2 pi I integral f of z dz divided by z minus a power n plus 1. Now, this expression here, we can write this one as, so this is just by definition. So f of z is, the first term is the same as f of a. Remember here, when you define f of a, alone will be now 0 factorial is 1, so 1 over 2 pi I integral of f of z dz over z minus a. So when the value of n is 0, so the function at a is given by this. So using these formulas, you see the first part here is exactly the same as this one, only that now this is taken by t, this is t, this is t. So this will be given by f of a. And then if I factor out z minus a, so I'll have here as z minus a, then 1 over 2 pi I integral of f of t dt divided by t minus a power, these two can be written as 1 plus 1. So the value of n will be 1. So the first derivative. So it's like I have z minus a multiplied by the first derivative at point A. So using this definition of the Cauchy's integral formula. So the next term will be z minus a. So we have f of a plus z minus a times f prime at a. And then next here, this I have this one as I factor out z minus a squared. And then I have integral of f of t dt. Then here I have t minus a power 3. So let's just demonstrate how this one is giving us the next term. So if I have z minus a squared times 1 over 2 pi I integral of f of t dt divided by t minus a power 3. So you see in this formula here, nth derivative at a is n factorial over 2 pi I integral f of z dz over z minus a n plus 1. So if I remove this n factorial here, then the formula can be written as nth derivative at a divided by n factorial is the same as 1 over 2 pi I integral of f of z dz divided by z minus a power n plus 1. So which means this value alone is the same as, remember 3 can be written as 2 plus 1. So the value of n will be 2. So this is the same as writing the second derivative at the point a over 2 factorial. So this is what this expression will be defining. So then multiplied by z minus a power 2. So therefore, the next term will be z minus a power 2 divided by 2 factorial. So you'll have plus z minus a power 2 over 2 factorial times the second derivative at a. And then next term will be given by, you factor out z minus a power 3 so z minus a power 3. And so here we'll have now f of z dt, f of t dt over t minus a power. So this 4 can be written as 3 plus 1. 3 plus 1. Then we have integral 1 over 2 pi I. So similarly, if you want to have 1 over 2 pi I, so it means that you need to divide here by n factorial. So we'll not have this n factorial here. So n will be 3. So we'll have the third derivative at a divided by 3 factorial. So therefore, we'll have 3 factorial, then third derivative at a, and then we can now predict the next term easily, which will be z minus a power 4 divided by 4 factorial times the fourth derivative at a. So the next term will be given by z minus a raised power 4 over 4 factorial. So plus z minus a power 4 over 4 factorial, fourth derivative at a, all the way plus z minus a power n over n factorial, nth derivative at a, plus its other terms. So this is what we call the Taylor series. which is the required Taylor series of f of z about the point z equals to a. So this series converges to f of z for every z lying within the circle C. So that's how we prove the Taylor series for function of complex variable f of z. So if we put z to be a plus h, then the series can be written as f of z equals to f of a plus h. And so remember, when you say z equals to a plus h, is the same thing as saying z minus a equals to h. So therefore, we'll have f of a plus, instead of writing z minus a, we write h times the first derivative at a plus h squared over 2 factorial times f double prime at a plus h cubed over 3 factorial, third derivative at a plus h power n over n factorial, nth derivative at a plus other several terms. Now, putting a to be 0, the series becomes f of z equals to f of 0 plus z f prime at 0 plus z squared over 2 factorial, second derivative at 0 plus z power n over n factorial, nth derivative at 0 plus other several terms. And this is called Maclaurin series of f of z. This is how we prove the Taylor series. So the key thing is to remember the Cauchy integral formula, and then use the Cauchy integral formula to simplify this definition of the function f of z by creating a circle around the point z, and then reduce that integrand into a series that will eventually be reduced to the same terms given in the right-hand side of this expression here. So next we do examples to illustrate how to expand a function in Taylor's series. Thank you.